Hey everyone, following the last tutorial, I've had some great questions on user mode and kernel mode. So, I thought I'd take the opportunity to do a deep dive on what they are and how they work from the hardware up. Some of what I'm about to cover is outside the scope of this course and is purely to help your understanding of the concept. You can refer back to the lecture notes and book to check what is covered and what will be examinable. Modern CPUs have several modes of operation, where each mode of operation gives access to a specific subset of the CPU's instructions, as well as limiting memory access locations. These exist to protect data, provide fault tolerance, and system security. The most commonly used of these are supervisor mode and user mode. Supervisor mode, commonly known as kernel mode, is usually the least restrictive of these modes, in which the CPU can execute any instruction and has full access to memory and I/O. This allows processors in kernel mode free reign of a system, allowing them to do things to remap memory for themselves and other processors, read and write directly to storage media, and enable or disable hardware. In user mode, typically the most restricted mode of operation, the CPU has access to a much more restricted set of instructions and subset of memory. So when we say the operating system runs in kernel mode, we're saying that while the OS is performing its various tasks, the CPU is operating in supervisor mode. And similarly, processors running in user mode have a restricted instruction set and memory because the CPU is operating in user mode while they're running. So what does this mean for operating systems? To be able to manage things like virtual memory, device drivers, and process scheduling, the core functionality of an operating system must always run in kernel mode. That is to say, the CPU must be operating in kernel mode while these processes are being executed. When we want to run a program in the more restricted user mode, the initial state of the program, as well as its mode of operation, is loaded into the stack, and a CPU instruction to load the state from the stack and continue executing is issued. From this point, the CPU is in the new mode and executing the new process. So that's how we switch from kernel to user mode. But how do we get back? We know we'll have to switch back to the OS eventually, but surely a process running in user mode shouldn't be able to switch the CPU's mode back to kernel mode. That would defeat the whole purpose of the security. The way that we do this is using interrupts and traps. You might recall that interrupts are hardware events that occur when system hardware sends a signal to the CPU. And traps, also known as software interrupts, are software events that can occur under a number of conditions. When one of these events occurs, it raises one or more flags in the CPU. When the CPU detects the presence of a flag at the start of one of its cycles, it will pause execution of the running program and push its state to the stack. Then, it will switch to kernel mode and begin executing an interrupt handler, behavior defined by the operating system. Because the CPU has paused execution of the program and completely handed control over to the OS, we maintain separation of privilege modes. Once the OS has control again, it can save the user process's state for later and schedule a new process to run. It can service a system call or respond to a hardware event such as a keyboard press. When the OS is ready to switch back to the user or some other process, it again loads the process's state, which includes the mode of operation, back into the stack, and once again runs the CPU instruction to load state from the stack and continue.